Okay, different cases. So we can do that. We also say if I got 3x plus 2 equals say 7, we just follow the same process. We add its opposite. We know we can do that. And then 2 plus -2 is 0. So we got 3x plus 0 equal to 5. And then 3x plus 0 is just 3x. Then we got 5. Then we just multiply 1/3 on this side. So that become 1x and it become 5/3. Okay. Which is x equal to 5/3. And because once we know this 3x plus 0 is just 3x, we can basically skip this step. Okay.
Yes.
And we know 1x is just x, so we can skip this step. Okay. But you just have to know that that's the step there. We just we don't have to write it out, because if you're doing math, you're supposed to know this. Good. Okay, so I'm going to show you a couple more, and then we're going to come up with a formula. Okay.
Okay.
Okay. So let's say 2x minus 7 equal to 10. Okay. So -7 in algebra is the same as plus -7. Okay.
Okay.
Good.
Yeah, got it.
Okay. So in algebra, we're dealing with addition and multiplication. Okay. The two we're dealing with. So subtraction we can write as like -5 is basically the same as adding -5. Good.
Got it.
Okay. So we're going to add the opposite. The opposite of -7 is just 7. Then we add 7 here. And what we got, -7 plus 7 is 0. 0 plus 2x, it's just 2x. On this side, 10 plus 7 is 17. Then we're going to multiply half on both sides. Then this side on the left, half times 2 is 1. 1 times xx, so the x is equal to 17/2. Good.
Got it.
So now you can see that it doesn't matter what kind of problem we have. The step is pretty much the same, right? Good.
Yeah, got it.
And if the same process, the process is the same, then we can actually come up with a formula, so we don't have to do this over and over. Good. So that's the power of algebra. Is okay. Instead of dealing each individual linear functions, we just say, okay, there's a general form of that. The general form is a times x plus b equal to c. Okay.
Got it.
So this is a number. It's called coefficient, and this is a constant, and this is a constant. Okay.
Got it.
And we have 3 terms. Those are called terms. 1, 2, 3. Good.
Got it.
And b and c are called constant because they don't change. And ax, they will change, right?
Yeah.
And so the a here, even the a is also a number, just like b and c, but this is a multiplier. So we call this coefficient. Good.
Got it.
So now we have to end up with here, right? That's our end zone. We'll get it. So what we're going to do, follow the same process. We're going to add the opposite of b, which is -b. Good. Okay.
Got it.
And then we know b plus -b is 0. It doesn't matter what the b is, but a number plus the opposite is 0. So what we got is ax on this side is C plus negative B, and we know this is the same as C minus B, right?
Got it.
And then we're going to do times one array, and therefore we have to do the same thing on this side. Now, 1 over a times a is 1, and 1 times x is x. So we got x is here. On the other side, c minus b times 1 over a is the same as c minus b divided by a. Good?
Got it.
So now we got a formula. Okay, and this is what the power of algebra is, that we don't see any numbers here, but we have letters to represent numbers. Good?
Yeah. I can see how, like in physical science, I think there's like a formula for work or something, work or power, and it looks something like this.
Exactly. So Newton's formula, you have the force is mass times acceleration. Remember that, right?
Yes.
Yeah. So that's in science or in engineering is all about formula. Good.
Yeah.
And how to play with formula, and that is algebra. Good. So we use language and also what do you call that? The procedures of algebra. Okay. So we have this. Good.
Yeah.
Now we say, okay, it doesn't matter what kind of linear function there is. We now know how to just one step to get there from here to here because we worked it out. Good. Okay, with that, then we can use it. So let's say 2x plus 3 equal to 9. And now we don't have to go through that. We just jump down to this formula. C is 9, B is 3, A is 2. So that gives us 6 over 2, which is 3. So we just get there right away. Good?
Yeah.
So that's actually what algebra is to play with symbols so we can came up with a form. And then we use that. Good? It does make things a lot easier, right?
It does.
Okay, let's see if we have something like, say, negative 2x minus 4 equal to, say, 10. And then we just use that. Then this is 10 minus negative 4 and divide by negative 2. So that will give us 10 minus negative is plus, so it's 10 plus 4 over negative 2, and that's 14 over negative 2, which is negative 7. Good. So now we just use formula, and you'll see that later on when you're dealing with more algebraic problem in algebra, we use formula a lot. Good. But the point for us here is not learning or memorizing the formula. And what we are trying to learn is how to derive the formula. Okay.
Yeah, that makes sense.
Yeah, because that's a skill you need later on when you're trying to solve new problems. And so, especially nowadays, we really don't need to do something like this anymore because we have computers, right? So anything repetitive is going to be done by computers, but anything creative that's done by us humans. Good?
Yeah.
But in order to be creative, we have to follow the rules. That otherwise, it won't be something nice, right?
Yeah.
Like say you design a building, and you have to follow the rules. You have to follow the physics.
Yeah, or it's gonna fall apart.
Yeah, it's gonna fall apart, and also it won't look nice either.
Yeah.
So now in architecture, you're dealing with a lot of geometry. You're talking about you know, symmetry and proportions and things like that. Okay, so this is kind of our linear equation. So basically, once we got the formula, we are done with the linear equations. We know how to solve it, right? Yeah. Okay. Now I'm going to give you a couple for you to work on. So we have ax plus b equal to c. We know that. Our answer would be c minus b over a. Okay, so let's see. 5x minus 7 equal to 9. So what is our x? Okay.
Okay, let's see here. So c minus b over a. Okay, so x is equal to c9 minus 7 over 5. This is a 2 over 5. 2 over 5 the correct answer?
Let's see. Now, what is our c?
9.
9. Okay, the 9 minus b. What's our b?
B is 7.
It's not 7. Look at here. This has to match this. So minus 7 is 5 plus negative 7.
Yeah. Minus negative 7s. That would be, yeah, that would be 16.
Right, 16. 5. Very good. Okay, so let's see. Negative 3x minus 4 equal to negative 6.
Okay. X is equal to 9 over 7. Okay, so
not meant to be distractions.
Yep. So x. Now we just need to figure out what is our c, what is our b.
Wait, no. B would be negative 4. C would be negative 6. And A would be negative 3. So that would be
Very good.
negative 6 plus 4. Negative 6 plus 4 would be negative 2. Negative 2 over negative 3. That would be basically equal to 2 over 3, right?
Right. Yeah. Negative divided negative is positive. So we got that. Good.
Got it.
All right. So you can see here, when we're dealing with algebra, we're also talking about the numbers we're dealing with. So in algebra, what kind of numbers are we dealing with? So it's kind of like a good review back. So the first number family is called counting number. So we got 1, 2, 3, 4, and so forth. Good. And that's how people know, I mean, early people knows about that, is how they know how to count. And then from there, we add a 0 to it. Okay.
Yeah.
And this is called whole number. And this is very important why we had zeros there. Okay. Whole numbers. Because without 0, we really cannot do something like that. Okay. And something like that. And you can see this interesting. We have the same symbol here.
Yes.
Do they have the same value?
No.
and this is 20, right?
Yes.
And this is 200, right?
Mhm.
And this is 2000. So even though the same symbol, the value is different. And this is called the place value. Good.
Yeah.
So the value, this is a 2 by itself, is called numeral. Numeral 2. It could be 2, could be 20, could be 200 or 2000. Really depends on its place. Good.
Yeah.
And the way we put it in place is by adding zeros. Okay.
Yeah, got it.
And so sometimes we take something like here for granted. Okay.
Yeah.
You can see here's same numeral, but this is value-wise, this is 2. And this value is 20. This value is 200. Good.
Yeah.
Exactly same numeral, same symbol, but have different values. And that is because we have a concept of 0. And that's really get into what algebra is. Good.
Yes.
Okay, algebra now has really, we're using symbols to represent numbers. And in the old days, not like this. If you look at Roman numerals, and this is 1, it's always 1. And this is 5, and always 5. And this is 10, is always 10. Okay. And the way we write in terms of Roman numerals is this is 1, then this is a 2, this is 3. So far, so good. And then we say, okay, what is 4? 4 actually is 5 minus 1. So it's 1 here, 5 is here. But something smaller, 1 is in front of it, is subtraction. Okay?
Yeah. Yeah.
And this is 5, and this is 6, this is a 10, this is not. Oh, sorry, this is 6, 7, 8. And then when we got 9 is actually 1 of 1x, it's 10 minus 1. Okay.
Yeah.
And then we got to 10. So that's what people used to do before, until about 1,000 years ago. And people use this to record numbers. Okay.
Yeah.
And now, if we want to go count more, then we say, okay, this is 10, this is 20, this is 30. And then we're going to invent something called 50, it's L. Okay. And then we got 60, 70, 80. Then we have to invent something called 100, which is C. And then we got 100. Good.
Yeah.
So now we have that. But the problem is, because the symbol I is always the same, X is always the same. Now, if we're going to have bigger numbers, we'll keep inventing. We're going to keep inventing numbers, right? Like say this is 500 and this is 1,000. Good.
Got it.
Keep adding. Then once number got bigger, we pretty much run out our letters pretty soon.
Yeah.
Good.
Yeah. Yeah.
But with this kind of numeral, all we need is 10. All we need is 10 numerals, and that's it. And we can use that to represent any number we can think of. Okay.
Yeah. Yeah, that makes sense.
Yep. So that's why we use this now to calculation. We don't use this. It's very hard to use this to any calculation. But use this, everything lines up. Like say 230 plus 125. We just line them up, right? Because this is 0 plus 5 is 5. And this is actually 30 plus 20 is 50. Good.
Yeah.
And this 200 is 100, it's just 300. So we have 355. Good.
Yeah.
Yeah. And then we just, when we add, we just try them as single digit. 0 plus 5 is 5, 2 plus 3 plus 2 is 5, 1 plus 1 is 3. So make things a lot easier.
Yeah. That makes sense.
Yep. And this is kind of very revolutionary. And before that, the way people can do calculation, they have to use some kind of tool. It's called abacus.
Abacus. Oh, I've heard of those.
Yeah, because they won't be able to do that, just write it out. So they have to use some kind of tool, kind of like their calculator. Good.
Yeah.
But once we have Arabic numerals, everything changed. And also from the Arabs, we actually learned, that's where the algebra came from. Okay.
Got it.
And they are, in turn, they got that actually from ancient Greek. Okay. So they actually translate a lot of ancient Greek texts into Arabics, and then the Europeans learned from the Arabs, from their translation from ancient Greek, because ancient Greek, the books and all that, most of them were destroyed or lost. So we learn, actually, the Europeans learn from that. So that's why this numeral is called Arabic numeral. Okay. But actually, the numeral was not invented by Arabs. The numeral was invented by the Indians.
Indians?
Yeah, in Asia.
Okay.
Yeah, so this actually, now we call this Arabic Indian numeral. Okay, India has produced many great mathematicians, and they do have an Asian history, and they were very good with math. Okay, so now we have there's 1, 2, 3 counting numbers, then we have whole numbers, then we have something which is unique, is what very important concept in algebra is called integers. The reason for why it's important is now we have something abstract. It's called negative numbers. So now we understand those positive numbers, right? Hello?
Yeah.
Right? We see them, we count them, even though they're abstract, but at least we can count them, we can grab some 5 apples. And negative number is purely abstract. Because there is no way you can have negative 4 apples, right?
Yeah.
You won't be able to find them. You won't be able to buy them. But as numbers, since we are just do calculations, then we can have something called negative numbers. And that makes our whole thing, calculations become easy. So that's why in algebra, we only have add. We don't, that covers everything. When we have the rules algebra, we just concerned about addition and multiplication. Okay. Yeah. Because anything subtract can become, say, 9 minus 5, that can become 9 plus -5. Good?
Yes.
And now we have very nice, remember we have this A plus B is equal to B plus A, right?
Yes.
That's the community property. Now, once we have negative numbers, we can easily do that. That's the same, give us same result, right?
Yes.
But if you swap this, we'll have different value. That's not the same as 9 minus 5, right?
Yes.
So now we have negative numbers, it makes the mathematical problems a lot easier. And of course, then that math is a foundation for all the sciences. And so, and then of course, engineering is built on top of the sciences. But it's all because now we have not only positive numbers, we also have negative numbers. Okay, and that's called integers. So next time we're going to talk a little bit about rational numbers and real numbers, because that's basically, then we have imagine numbers, and then that's all the numbers we are working on in algebra. Good.
Got it.
All
Thank
right.
you very
No problem. I'll see you next time.
much. See ya.